The scene I am analyzing today is from the 2003 movie Too Fast, Too Furious, starring Paul Walker and Michael Ealy. Here's the clip, raw and unedited.
Alright, y'all see that? Told y'all I had a surprise. How you like that for a finale?
Bridge.
My objectives are to solve for both the car's horizontal displacements, delta dx, and their time spent in the air. The first thing I did was find the measurements of the bridge. In the part of the scene pictured, the bridge is shown from a side view, making it possible to estimate theta. I estimated that theta is about 30 degrees. However, I need the ramp's length in order to calculate the car's vertical displacement. After determining that the scene was filmed on the South Miami Avenue Bridge, I was able to research the bridge's horizontal clearance. I found this to be 90 feet. However, this didn't mean that the length of the ramp was 90 feet, because not all drawbridges open equally on both sides. So I checked on Google Maps to see if there are any clues indicating whether or not both sides of the drawbridge are equal. This crack in the railing marks the halfway point of the drawbridge. After zooming in, I could see that there are groups of screws located equal distances away from each other. On the left side, the screws appear 9 times. On the right side, they also appear 9 times, meaning that both sides are equal. So, to calculate the length of the ramp, I need to divide the horizontal clearance by 2. This gave me 45 feet or 13.716 meters. Now, using sine law, I was able to determine the car's vertical displacement, which was negative 6.858 meters. With this information, I move on to the next portion of my calculations, which was solving for the force of kinetic friction acting on the cars. I need to solve for the kinetic friction of both cars because the initial velocity was given to us at the bottom of the ramp, and due to all these forces acting on it, especially kinetic friction, the initial velocity of the car will be different to the final velocity of the car on the ramp. The values that are known to me already are the coefficient of friction between rubber and asphalt, which is 0.7. I also researched the mass of the Nissan Skyline plus Paul Walker the actor, which is about 1398.5 kilograms, and the mass of the Toyota Supra plus Michael Ealy the actor is about 1625 kilograms. These values I was able to calculate for the normal force acting on both cars. On the gold car, I calculated the normal force to be 13,791.45 newtons, while the silver car's normal force was around 11,869.14 newtons. These calculations make sense because the silver car's mass is smaller than the gold car's. Next, I calculated the force of kinetic friction acting on both cars. Using the equation Fk equals mu k Fn, I found that the gold car was facing 9,654.015 newtons of kinetic friction, and the silver car was facing 8,308.398 newtons of kinetic friction. With these values, I moved on to the next step of my calculations, finding the work done by friction and using the law of conservation of energy to find the final velocity of the cars on the ramp. Using the equation Wf equals Fk delta d cos theta, I was able to calculate the work done by friction on the gold car to be 114,674.29 newtons, and on the silver car it was 98,690.51 newtons. Using the mechanical energy equation, I calculated that the gold car's final velocity was about 51.006 meters per second, which I rounded to 51.01. This is the correct velocity compared to the initial velocity of 53.64 meters per second shown in the clip. Using the same equation, I calculated that the silver car's final velocity was 71.87 meters per second compared to its initial velocity of 73.76 meters per second, also shown in the clip. After solving for the final velocity of both cars, I moved on to the final phase of my calculations, finding the horizontal displacement of both cars as well as the time spent in the air. I based my calculations around this projectile motion diagram, where VI is the VF we just calculated. I first solved for the gold car's time in the air, and I found that it spent around 5.46 seconds in the air. With this value, I was able to plug it into the equation delta d equals vix delta t plus 1/2 acceleration delta t squared, which simplified to delta dx equals to vix delta t. And this gave me the gold car's horizontal displacement of 241.22 meters. Next, using the same equation, I found that the silver car spent 7.519 seconds in the air, and I plugged it into the same equation of delta dx equals vix delta t, and I found that the car displaced 468.025 meters. Finally, I've reached the comparison of the scene versus reality and the conclusion. First, I compared the airborne times of both cars. Upon timing the scene, I found that the silver car spent 7.19 seconds in the air, while the gold car spent 8.37 seconds in the air. According to my calculations, the silver car spends 7.519 seconds in the air, and the gold car spends 5.46 seconds airborne. The silver car should have spent almost 2 more seconds in the air than the gold one, unlike in the scene. Is this accurate? No, it is not. Next, I compared the displacement of both cars. In my calculations, the gold car travels 241.22 meters, whereas the silver car covers a much larger distance of 468.025 meters. But what about the clip? Here you can see that the two cars land just meters away from each other, rather than the 200 meters of distance that they should have between them. Is this accurate? Once again, no, it is not. So, after all my calculations, does Too Fast, Too Furious obey the laws of physics? No. Unfortunately, this epic scene was not created with the special touch of a physicist.